we talked about how we would use conservation of charge and its role in circuits with a single and multiple path. So that's what we're going to talk about right now. And this is a part of what your Google form discusses, okay? So remember, conservation of charge. So conservation of charge means that we cannot create or destroy charges. We cannot suddenly create a positive charge here or a negative charge there and make it do something in the circuit. Whatever charges we have, we will always have. We cannot create or destroy them. So if we go here, I'm gonna turn the current on. So now we see all these little charges present. It's showing them as negative, so it's kind of like we're thinking about electrons. So now we can see all of these charges that are present. They don't start at the battery, they exist everywhere. What the battery does is motivate them. And now here, we don't have any splits. So this is all a single path. Everything here is what we call connected in series. There's a wire. After the wire, it has to go through the ammeter. After the ammeter, it has to go through the wire. After the wire, has to go through the bulb. After the bulb, there are no splits. Has to, when the switch is closed. Close the switch, oops, close the switch, and the charges have to go in this direction through what they're doing there. That's really slow. Oh, because I have a bunch of crap going. A bunch of tabs open. We'll do that so we can like see the charges moving. So since we only have one path, or if we think about it as people in a hallway, every person that enters here has to go through here and has to exit here, right? A person into the hallway here means a person out of the hallway there. They're all just lined up back to back to back. You're never going to have a person enter this hallway and disappear and not come out of this hallway. Not unless you're watching a weird show, right? I mean, in reality, that doesn't happen. Every person in here goes out there. This battery won't let people go back this way. It forces them that way. So one path, the current is the same everywhere. If a person goes in here, a person comes out there. Once this person goes in here, they walk through the hallway, they come out here, they're now in this hallway, they walk through this hallway, right? If we can think of every one of these little blue electron thingies here as being like a person. Person goes in, person goes out, no options. We're right at the time. Give me a second. I want to make sure you see this next one. Hopefully you have time. There used to be a pause button on these things. So I'm going to go to this one now. So this one now, not all in series, right? There's a split. This junction right here is a split. So current comes in or charges can go in, and then at this junction they split. Some go up, some go down. So if we show current and we close the switch, so now what we'll see is that we don't have the same amount of current everywhere. If you can give me like 90 seconds, I think we'll put you in a good spot for the rest of the day. So now here we have all of the people walking through these hallways. They can't go back because this battery is motivating all negative charges to go this way. So you can't go back because this won't let you go back. When you're here, every person that goes in here has to come up, has to go up, has to go up. But now this spot is what we call a junction. It's like a split in a hallway. You can either go up or over. Either way, but it doesn't have to be just one way. There's an option. Some charges can go this way, some charges can go that way. And this law of conservation of charge says that, hey, if we have 1.8 amps of current, or like on average 1.8 people in per second here, then there's 1.8 people in per second here, there's 1.8 people in per second here, and if there's 1.8 in, that means there's also 1.8 out. We get to this junction, and if there's 1.8 people per second in, then there's also 1.8 people per second out. 0.9 this way, 0.9 this way. It splits up even Steven on this one. If I change this bulb so it behaves differently, these are now different light bulbs. Yeah, so now these are different light bulbs, and you'll notice that's awkward numbers, but it'll work. So now this has changed to 1.07. I wonder if I can make these numbers a little bit easier to deal with. Come on. Sorry, folks, I'm trying to get this done real quick. Like, is that any better? It's not. I thought I could get that to round them off. If I make this 10, that might help. There, that helps a little bit. Yeah. Okay, so now we have 1.2 people per second into this ammeter, 1.2 people per second out. 1.2 people per second into this corner, 1.2 people per second out. Now here's another junction. 1.2 people per second in. Well, 0.2 people per second, right? We're not cutting people into 0.2s, but 0.2 people per second go this way, and 1 person per second go this way. Yeah, and now they get here again, and they join up. So if we have 0.2 people per second here and 1 person per second here, they merge, and then we have 1.2 people per second here. That is the conservation of charge and how conservation of charge relates to these current things and the junction rule. The junction rule says that the total current into this junction should equal the total current out. I have 1 amp in and 0.2 amps in, so that means I have a total of 1.2 in. I have to have a total of 1.2 out. I hope that makes sense. I'm sorry, I went really fast on that last part and I went really slow on the other part. My apologies. I'll stop now.